In 3A part 1 we have a solid wooden sphere and we're to describe and explain how we can measure precisely the diameter. Well, we'd use a vernier caliper or a large micrometer, as standard micrometers measure to a maximum of 25 mm, and this is 28 mm, and we'd measure in several directions, then calculating a mean. In part 2 we're to show that the mass is 0.0075 kilograms. Well, density is mass over volume, so mass is density times volume, which is 650 kilograms per cubic meter, times the volume of 4/3 pi times the diameter of 0.028 over 2 to get the radius cubed. And this comes out at 7.5 times 10 to the minus 3 kilograms as required. For part 3, the sphere is now pushed below the surface of water. We're to find the force that needs to be applied to the sphere to keep it stationary under the water of density 1000 kilograms per cubic meter. Well, upthrust is equal to the weight of water displaced, and this is density times volume, which gives the mass, times the gravitational field strength, which is 1000 kilograms per cubic meter density times 4/3 pi times 0.028 over 2 cubed again, times gravitational field strength of 9.81. This comes out at 0.113 newtons. The weight of the ball is mass times gravitational field strength, which is the mass we found a minute ago, 7.5 times 10 to the minus 3 kilograms times 9.81, which comes out at 0.074 newtons. So the additional force acting down, we have the ball like this, with the upthrust acting up, the weight acting down, and we want another force acting down, which will be the upthrust minus the weight, and that is then 0.113 minus 0.074, which comes out at 0.039 newtons. In B, we're given the equation speed v is equal to a constant times the radius squared for the terminal velocity of a metal sphere as it travels through a liquid. We're to describe with the aid of a suitable diagram how an experiment can be safely conducted and how the data can be analysed to determine the constant k. Well, we'd need a long tube, something like this. Do my best to draw some nice straight lines. And that would need to be filled with a fluid. And then we'd need markers, so we could have a marker like this, and another marker here, and another marker here, and these markers could be a equal distance d apart. So if this is a distance d, and this is the same distance d, then the time to drop down here, t1, and the time to drop here, t2, could be found. And if t1 is equal to t2 for several attempts, then we've reached terminal velocity. Okay, then we could have, so we know that from this point we have terminal velocity, we could then have another marker near the bottom of the tube here. The longer the distance possible, the more accurate the measuring. So this then I'll call h for the height the ball is falling, and then we can find the speed as the distance h over the time t. To carry out the experiment, we'd measure the diameter of the spheres using a micrometer in several directions and find the mean. We'd then use a meter rule to measure the distances shown on the diagram, and we'd either use a stop clock or maybe a light gate and a timer to measure the time to pass between the markers. We'd time several drops for each sphere and find a mean. We'd repeat this for spheres with a range of diameters. We'd plot a graph of speed against the radius squared, not forgetting that the radius is the diameter over 2. K is found from the gradient of the graph. To stay safe, we'd need to use a tray to catch spills, and we could use a magnet on a string to retrieve the spheres.